So, as I was talking about the electromagnetic spectrum that reaches from the sun to the earth, okay, that follows Planck's distribution. The black body radiation, as I was telling you last time, is given by this line, this very slight line, this whole thing here. Okay. It is the black body radiation. Now, what do I mean by a black body? You can think of a black body to be a sphere, a cavity, basically a spherical cavity, something like this, a spherical cavity which has maybe a coating inside which a reflective coating or an absorbing coating, partially it can be partially reflecting, so that a bit of light that comes through gets reflected within and gets absorbed there itself. Okay. It is trapped inside this cavity. Or you could think of it as a spherical ball which has coils outside, so that it gets heated. Here in this picture I have just shown the coils here. Okay. Once it gets heated, that means the inside is radiating, but that radiation is not allowed to go out. This hole is very tiny here. So, now you want to know what is the distribution of this radiation which is trapped inside. So, that is what is a black body, and the distribution of this black body, this cavity, this hollow cavity, distribution of the radiation inside follows the same path as this dashed line. Okay. And that is given by the Planck's formula. So, that is the correction between not correction, that is the connection between the black body and the sun's radiation, and it is given by the Planck's formula here. Here capital T is the temperature, as I have written here, and small t is the oscillation period. Okay. And it gives you the distribution of these frequencies which is given here, and h is the Planck's constant. Okay. So, now that is what the radiation is about. Now, let me just tell you the spectrum of this electromagnetic radiation. I have just put it down in a chart here in different regions. So, suppose I take the visible region, which has wavelength, you can give it in angstroms. So, that is the visible goes from 7,000 to 4,000 angstroms. The wavelength can be given also in centimeters. So, it is given as 7 into 10 to the power minus 5 centimeters to about 4 into 10 to the power minus 5 centimeters, and in frequency too. Okay. So, the spectrum is given in terms of frequency or in terms of wavelength and or in terms of energy, because h nu is that corpuscular energy of that bit of photon. So, E energy h nu, which I have said in the previous slide, is given in terms of this. So, here you have different regions, the radio frequency region, the microwave, infrared, visible, ultraviolet, up to the gamma ray. And here you can see, and these are the energies that corresponds to a gamma ray. This is the energy that corresponds to a X-ray. To the visible 2 to 3 electron volts corresponds to the visible light, and so on. Now, now you would say that frequency, it can range from nu equal to 0 to nu equal to infinity. So, is nu equal to infinity possible? If nu were infinity, then the energy would be infinity too. That is also impossible. So, there is an upper limit to the energy and therefore to the frequency. But is there a lower limit to the frequency? Not really. The lowest frequency that has been recorded is around 8 hertz. Okay. So, you can consider that as a limit or something more to be discovered later on. So, here I will be explaining to you how the laser properties or the radiation from a laser is different from usual ordinary light that is coming from the sun or other bulbs or tube light or anything, other sources of light. How is the laser light properties different from those? First one is that lasers have very low divergence and it is very, very directional. That means you get a pencil thin light. If you have noticed on laser pointers, it just goes to a very large distance. Okay. It goes to this very large distance because the divergence is low, and it has a directionality. And of course, the laser light is almost monochromatic. So, if I have a red laser, it almost has that red frequency on it. Almost I say because it is not a delta function. Okay. So, it is almost monochromatic. On practical purposes, I think one can assume that. And light exerts pressure. Pressure is equal to 2 IC. I is the intensity of the light and C is the velocity of light. And so, pressure is exerted, and with lasers you can go up to very high intensities. That means you can exert a lot of pressure with light, just like Arthur Ashking did in his Nobel Prize winning work, where he made them into tweezers, used the pressure of light to make tweezers, light tweezers. Then the intensity of this laser light is proportional to the electric field, E square. I is proportional to E square. That means the electric field that is associated with the laser light is very, very large, and those also have some very exotic applications which we will see later on. Now, the most important property of laser light is its temporal coherence and spatial coherence. This is a very important property, and in order to understand that, let me describe to you Michelson's interferometer and Young's double slit experiment, which you may have come across somewhere in your high school days. Okay. So, in a Michelson's interferometer, what we have is a source of light here, source of light, 2 mirrors, 1 beam splitter and the detector here. So, all these things are sitting on a rail and they are fixed. Okay. So, basically mirror 2 is fixed, you can keep mirror 1 moving up and down. Okay. So, you have a light source and the photons bounce from the mirror 1 and back here is split into 2, the photon that is coming out from here. So, Michelson's interferometer is an experiment which demonstrates amplitude division of light that can give rise to interference pattern. So, whatever is the light here, you have divided it equally here and here, and then they combine here again and you get an interference pattern. So, if this alignment is not right, you will not get an interference pattern, you will get a blob of green light here. Green light is just an example, it could be red also. So, what I am assuming here is that my light is monochromatic, because if you do not have monochromatic light, you perhaps may not even get interference fringes. So, now we are concentrating only on the temporal coherence. Okay. So, I assume that the light is monochromatic. Now, okay, this is a movable mirror. So, I move this mirror up and down very carefully, as we had done in our school days, and you see that these fringes will disappear at a certain length. Okay. You keep moving up and down, at some point it will come back and some point it will go off. This is what will describe temporal coherence. Why does it go off and come back? That is because the photon or the light is not temporarily coherent. It is not temporary coherence in this following way. Suppose I have a train of light. Okay. This is a train of light, and this train has a time duration of tau c, okay, or it has a length of c tau c, okay. This is how it is. It has a length of c tau c, and tau c is called the coherence length. That means when I am moving this, c tau c is called the coherence length and tau c is called the coherence time. Okay. So, while I am moving this mirror up and down, the fringe is disappear when it does not follow this tau c. The moment it follows tau c, c tau c, you will get interference pattern. So, I have say a train of light here. Train means, okay, this is a train of light, after that some other train starts, and I have another train which maybe is coming from this mirror, mirror 2, and it is identical to this train. When these are identical or nearly identical, see here, 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 the peaks and the troughs are matching, okay. That time you will get the perfect interference pattern. And for how long does this happen? That is the coherence time. And if you convert it into length, that is the coherence length. So, that is the importance of Michelson's interferometer in order to understand temporal coherence. Now, what happens since, okay, in this I can say that in case of lasers, the temporal coherence is much larger than ordinary light. If you compare with, say, a neon light and a laser light, the laser has a temporal coherence time in milliseconds, and the neon light has in picoseconds. So, that means the laser can be moved up and down, this mirror can be moved at a larger distance and you still get the interference pattern. While in case of neon light, you have to be very careful how much you move. So, it is easier to get it done with lasers. Now, what do I mean by spatial coherence? This is also Young's double slit experiment, which was done in our, say, high school days. You would have done it. So, you have a laser light here. No, it need not be laser light. It is an incident wave and it goes through a slit, and then you get these waves which are coming out here. It goes through a double slit and each of them are generating these wave fronts, and these wave fronts interfere with each other and you get a maxima, minima, maxima, minima, maxima, minima, and you get an interference pattern like this. This pattern is similar to this. Okay. So, this is what you get. Now, if you move these two slits apart, these two slits, you make a wider distance between them, you will find the interference is disappearing. Okay. Now, why is the interference disappearing? That is because there is no spatial coherence of these wave fronts. Okay. So, you know these wave fronts, suppose I create a wave front like this. Okay. Now, I have you know, this partition, and I have a slit here and I slit here, which is identical to these two slit spacing. Okay, that is what I have shown here, and they are both sitting on this. They are both sitting on the same wave front. Okay, this slit is kind of sitting on the same wave front. So, whatever is coming out of this slit and whatever is coming out from this slit, they have an identical secondary wave pattern which will interfere, and you get an interference pattern. But if I take, say, this slit and I put it somewhere here, that means now this slit and this slit, they are on two different wavefronts. Okay, this wavefront, it is not sitting on the same wavefront. So, there is very little, I will not say little, less correlation between this wavefront and this wavefront. Since they are not that well correlated, you will get a blurring of this pattern. So, as I take my slit further and further apart, the interference pattern becomes more and more blurred, and once I come back closer, the interference pattern becomes sharper and sharper. This is called spatial coherence. So, as we move away, the slits, we take them apart, we are moving on different wavefronts. So, the correlation of these wavefronts are not perfect, and so we do not get this pattern. Now, what is the difference between ordinary light, say a bulb, or again a neon light and say a laser light, is this. You can get this pattern very easily in case of a lasing, a laser light. You can take these things apart, okay, and still you will get the interference pattern. While in case of ordinary light, you know, this distance between these two is very, very important and very critical. So, that is because the laser light is also spatially coherent in addition to being temporally coherent, temporal coherence. So, with laser light you can sort of easily get this interference pattern, you do not have to be too careful, okay. You can have these things apart. So, now we can go towards the light amplification and some basic principles, okay. We are just going towards what should I say, how do I build a laser? You look at it that way. How do I amplify light? How do I amplify the photons that I am creating in a certain medium? Okay. So, we are moving towards that. So, what is the first thing that is to be known? The first thing that is to be known is that this laser light, the way it is to be produced. So, I have a medium. You consider that medium is consisting of atoms, molecules, particles, which have to be distributed into energy levels. Okay? Let us say this is my system. It has a whole lot of particles, and these need to be distributed into energy levels of this system. Why do you have these energy levels in this system? Because this is not at 0 degree Kelvin. This system has a certain temperature T, which is the average temperature. Okay. So, any body, it can be a room temperature or maybe slightly higher, and because it has this temperature, the atoms and molecules are moving up and down, they are continuously moving. Basically, these atoms and molecules, they have, I will call them particles for the moment, they all have certain amount of energy, and these energy are discrete energy levels. These discrete energy levels are E0, E1, E2, E3. So, the particles could be in E0 state, it could be in E1 state, it could be in E2 state, or it could be in E3 state. What would you think? Intuitively you would feel that most of the particles would be in the E0 state. So, most of the particles will be in this state. Okay. But there are some particles which have acquired certain energy, and they may be vibrating, oscillating, and they have a certain amount of energy. That is why they can make those kind of movements. So, they are in this E1 state. Then you have the E2 state, you have the E3 state, and as you go up the ladder you find the particle distribution there is becoming less and less. It is intuitive. Okay. The higher energy, the higher the energy, lesser the number of particles in that energy. Okay. So, now, but then mathematically you should have something exact. So, what is called is the Boltzmann's distribution. Boltzmann is the one who described how these particles will be distributed in all these energy levels. Obviously, the distribution will depend on the temperature, the average temperature. It will depend on the exact energy level state, and it will so basically we are looking for the number density of particles n. the number density of particles is proportional to E, it is proportional to T, and it is given by C e to the power minus E by kT. K is the Boltzmann's constant and C is just a normalizing constant. Okay. So, the Boltzmann's distribution gives you the exact number of particles, number density of particles in each of these energy level states. Now that we have decided how the particles have been put in each of these energy levels, okay. So, I will just take the lowest two energy levels 0 and E1 and show them here. This is 0 and this is E1. I am just concentrating on these two energy levels. Okay. So, this particle in this level can be absorbed and it can absorb an incident photon and it can go up to energy level E1. Okay. So, here is the incident photon. Now, this incident photon should have a frequency which is equal to E1 minus E0 divided by h. That is because remember we had seen before E is equal to h nu. So, here h nu is equal to E1 minus E0. So, the exact energy difference between E1 and E0, the photon should have that energy, then only this particle will go up to the higher level, which is the E1 state. Now, once it is in the higher level E1 state, it can on its own after some time just come down to the E0 state. Okay. And radiate. Where will that energy go? It had that extra energy, it has come down to a lower state, that energy has to be released. So, it releases some photon which has an energy E1 minus E0 which is the same as that, okay, once it is up there. But this particle which is here, it could also release its energy if it is nudged by another photon like this. Okay. And it releases, obviously if it comes down it releases its energy. So, there are two ways in which this photon which is there on top here and here can release its energy. So, the second one, it is called spontaneous emission, and the last one is called stimulated emission. It is like say you are sitting in your own house, okay, and you are thinking, should I go for a movie or should I not go? And maybe you go out for spontaneously you just decide and you go out and see a movie. But it could be that you are sitting at home and you do not want to see a movie, but then your friend comes along and nudges you and pushes you and says that let us go for the movie. That is called stimulated emission. So, you have spontaneous emission and stimulated emission. Now, all this radiation that is coming out, okay, it should follow a certain distribution. Okay. That means the specific radiation with nu, and nu as its frequency and T as its average temperature will follow a certain kind of radiation, which is called Planck's formula, and this is given by the Planck's formula here, and h again here is the Planck's constant which you came across before. Okay. So, we have a distribution of in the medium we have a distribution of these particles, and which is given by Boltzmann's formula, and we have a distribution of these radiation that is coming out from this medium, which is given by Planck's formula. So, it is important to remember the Planck's formula and the Boltzmann's formula.